All right, section 6.4 is called Ratios, Proportions, and Proportional Reasoning. And in particular, what you should notice in this entire section is that every problem that we're going to be working with, we're going to do a proportion for it. Now, I'm not laying claim to the fact that that's the only way to do the problem. That's silliness. Okay? There's going to be other ways to do the problem. But proportions are a really nice way of setting up problems because they have a specific pattern. And patterns are easy for kids to sort of get into the habit of where do I put things. Sometimes it's very tricky when you're talking about the language of mathematics to put things into an equation form because there's not that pattern in it, and proportions provide that pattern, okay? So everything that we're going to do in this section, you're going to do a proportion for. So resist the urge to do something different, okay? Try your hand at doing proportions as you work on these problems. All right, so to start with, a ratio can be written in one of three ways. It can be written with a colon between it, so we read that A to B. Or it can be written as a fractional kind of view, A over B. And either one of them, when we're talking about actually a ratio, we read this as A to B. Okay? So, for example, there are two ways of creating a ratio. You can create a ratio that is a part to a whole. So you're comparing part of something to the whole of something else. For example, there's 15 students in the class, 7 of them make an A. Then we would talk about the ratio of 7 to 15, A's to the whole class. Okay? Or we could talk about the ratio of A's, this is your part-to-part example, A's to quote-unquote not A's, people who got an A compared to those who did not get an A. And that would be 7 to 8 on this one. Okay? So there's two ways of doing comparisons, and we will come back to this. And I'm going to make a note of this when we do this right here. I think it's in chapter 10. It's 9 or 10. Maybe it's 9. I'm going to say chapter 9. When we talk, it's chapter 9 when we talk about something called odds. So we will come back to the part-to-part example when we talk about something called odds in chapter 9. It's an example of something that is a ratio that's part-to-part. And for that matter, this one is also in chapter 9, and it's when we talk about probability. So we will come back to these ideas later on. All right, so we're going to do an example. So we have a ratio of the class of boys to girls is 2 to 3. So we can convert between these two ways of doing ratios pretty easily. One way to think about it is to sort of set it up in like written form, that what we're comparing is boys to girls. And what we want is we want the boys to the whole class. Well, the whole class is boys plus girls. Agreed? So if the boys to the girls is 2 to 3, like this, then what would be boys to the whole class? 2 to 5. Now, it doesn't actually mean there's 2 boys and 3 girls, right? This could be a reduced fraction for something else. You know, so this could be 6 to 9 or something like that we've reduced down to 2 and 3. But the reduced form is 2 to 3, so the reduced form of the part to whole is 2 to 5. Or we could go the other direction, and you could also write this in this form if you prefer. It's the same thing, okay? Example 2, if we have 3/7 of the class are girls, then what is the ratio of girls to boys? Well, this is the same thing. We've got girls compared to the whole class to begin with. Well, what is the whole class? Well, the whole class is girls and boys, right? So if girls compared to the whole class is 3/7, and we want the ratio of girls compared to boys, well, the girls doesn't change, it's still 3. What would the boys be in this argument?
4.
It'd be 4, because it'd be the other value we need in order to take 3 and 4 to give me the 7. And again, if you prefer, you can write that in this colon notation too. Okay, so ratios can be part to part or part to whole, and you can be written either direction. And sometimes when we're working with proportions, it's helpful to write them in one versus the other, depending on the information given. All right, a few theorems about proportions. These are important. The first one says what a proportion is before we get to the theorem. A proportion is simply a statement that 2 ratios are equal. That's all a proportion is. So we have a ratio of A over B, another ratio of C over D, and a proportion says that they are equal to each other. That's it. Okay? Now, the next three statements are actually telling you, in essence, what you can do to sort of solve these equations somewhat, or to compare them at the very least. Okay? So the first one, Theorem 620, says that as long as the denominators aren't 0, you can cross multiply. Do you guys see that? As long as the denominators aren't 0, I can take A times D, and I can compare that by taking B times C, and I can set them equal to each other. It's really just the same theorem that we had back from section 6.3. But 621 is more interesting. In fact, it might look a lot like something I did on the board already today that you guys kind of panicked a little bit about. I'm giving Katie the eye over there because now I'm going to actually show it to you. All right. It says that if we have a ratio A over B is equal to C over D, we can flip them upside down, and they're going to create an equivalent ratio. So as long as I flip the left-hand side and I write it as B over A, I can flip the right-hand side and I can write it as D over C. See, I was allowed to do that, right? It was okay. But think about it. If you know, for instance, that 1/2 is equal to 2 over 4, don't you also know that 2 over 1 is equal to 4 over 2? You do. You know that you can flip those upside down. You may have not had any cause or reason to do so until now, but it's a perfectly legitimate thing that you can do. 622 is a little less intuitive. Starts out the same way. Again, all our denominator stuff can't be 0, just like the other two. We also have the additional consideration now that C is not going to be able to be 0. But if you have, again, this proportion A over B equals C over D, what do you see happens on the last piece here? What happened? What switched places? Say that again, Shelby. Yeah, I mean, that's kind of what it looks like. What switched in order for that to happen?
B and C.
Yeah, the B and the C sort of switched locations, didn't they? And likewise, while I don't have a theorem that says so, A and D could also switch locations and it wouldn't be any different. That would be the same thing. You know, switch one diagonal, you switch the other diagonal, it doesn't matter. And I will show you as we do some examples of why that works in a concrete sense. And you're going to go, well, yeah, of course that works. And you're going to know that you can do that because you've done it before. And it really has more to do with how you think about setting up a problem than it does anything else. Okay? So we're allowed to do two different things to get equal proportions. We're allowed to flip fractions upside down. Okay? Flip them both upside down. And we're allowed to switch diagonals. And you can switch either diagonal. It doesn't matter. Okay? All right, so let's do some examples of how that works. All right, Jim found out that after working for 9 months, he had earned 6 days of vacation time. How many days per year does he earn at this rate? So what I want you to do when you're looking at these problems is to figure out what things are being compared. So what things are being compared in this problem? Okay, so we've got the number of days off, and we're comparing that to the number of months worked. Do you agree? Okay, so one way to compare that in sort of a fractional sense is exactly like I just wrote it. So we can write numbers of days off. So how many days, we can write this as a proportion. How many days off does he currently have? 6 days. And for right now, I'm going to write the units in. I won't write them after I set it up, but just so that we make sure we get everything in the right place, it's usually helpful. How many months has he worked? 9 months. Okay, what's going to go on the other side of this? Yeah, this extra here is what we're trying to figure out. How many days is he going to have? That's what we're trying to find after 1 year, and Rachel already told us that we do need to write that as 12 months, which is actually absolutely correct. Now I want you to pause. We're going to solve this here in a second, but I want you to pause and think about it one other way. All right? Instead of comparing days off as a fraction where that's the numerator and the months worked is the denominator, what we could do is we could compare days to months like this. So what do I mean? Well, I mean we could put the days information all on the left. So right now he has, 6 days. What I'm trying to figure out is how many days will he have later. Right now he's worked for 9 months, and later he will have worked for 12 months. Couldn't we set the problem up like that too? Where the comparison is that everything on one side is one unit and everything on the other side is the other unit? Yeah, absolutely we could. Now this is exactly what's happening. Now take a look at just the numbers. Do you see the numbers here? 6, 9, x, 12, 6, x, 9, 12. What happened? Just looking at the numbers, what happened? X and 9 switched. That's a diagonal, isn't it? We can do that. I mean, we did it because we set up our problem appropriately, but in a different way. So it definitely is possible. The other reason I want to bring this up right now is because I want you to recognize that there are multiple ways to set this problem up that are correct. Okay, and these are not the only two either. There's at least 2 others. All right? The 2 others that there are is that you could be comparing sort of the future sense, basically like flip the fractions upside down, both of them. We could put the 9 months on top of the 6 days and the 12 months on top of the x days and vice versa on the other one too. And that would be perfectly acceptable. And any of those ways we do it, as long as we've set it up correctly, and there are 4 ways to do that, will give us the same answer. So you guys like to cross multiply. That'll be great. That's one way to do it. So let's do that because we didn't do that earlier. So if we cross multiply, what are we going to get? 9x equals 72. And then what? Divide by 9. So what will x be? 8. And 8 what? Days. Very good. You want to make sure when you're working with your problems here, these are problems with context, so the answer should have context as well, units. So this is 8 days of vacation per year. If you solve the other one, of course, the same thing happens. In fact, it very quickly looks identical, doesn't it? I mean, like the very first equation we write down looks exactly the same as the other one. Okay, is that all right? Okay, I'm not going to solve things 2 different ways every time, but I just want you to recognize that there always are more than one way to solve these problems. All right, let's try another one. On a city map, a rectangular park has a length of 4 inches. The actual length and width of the park are 500 feet and 300 feet respectively. How wide is the park on the map? So what are we comparing in this problem? A map versus real life, or feet versus inches is what Abby said, which is the same thing, right? One is being measured in feet and the other is being measured in inches. Do you want to set that up as a fraction or as a, feet on one side and inches on the other side? What do you want to do? A fraction? So you want to put something like real life on top, maybe you flipped it, I don't know, and then the map on bottom. Okay, so in real life, what other thing are we comparing? There's one other thing we're comparing in this problem. Yeah, you're actually comparing the length and the width. We had another comparison over here too. We didn't really talk about it, but the other thing we're comparing is now versus later. That's really what we were comparing here, right? Now, when we have the time off now, and later's amount of time off. So the length and the width. All right, so if we're going to do real versus map, we have to put the length on one side and we have to put the width on the other of an equation, okay? So all the lengths are going to be on the left, all the widths are going to be on the right. So if we do the real life, what is the length of the park in real life? Are we given that? 500 feet. What is the length of the park on the map? 4 inches. What is the width of the park in real life? 300 feet. And then the width of the park in the map is what we're trying to find. So that's the x inches down here. Now, part of the reason why we're putting the feet and inches in there at the very beginning is to make sure things line up. Okay? We should either have the same units on top, the same units on bottom, or the same units on the left, the same units on the right. we can't have a mixed up notation where they don't have that pattern. They're either top and bottom on both sides and they match, or the tops on both sides match, the bottoms both match. So we can cross multiply, right? At that point we can ignore the units and work out with the problem itself. So what do I get when I cross multiply? 1200 equals what? 500x, good. And then what? Sure, divide by 500. What is 1200 divided by 500? 2 point, what? You could write 2 2/5, that's fine. What might you also write? I'm going to be okay with you writing, this is real life, so you might also just write 2.4. It doesn't matter. Inches. And it is inches, right? Yeah, it is inches. Okay, let's try another one. Oh, Sheila and Dora, they're one of my favorite examples. Sheila and Dora, they work 3.5 hours and 4.5 hours respectively on a programming project. They're paid a total amount of $176 for the project. How much did each earn if they're both paid the same rate? So the first thing you have to do looking at this is recognize it really wouldn't be fair to give them the same amount of money, right? One of them clearly worked more than the other one, all right? So what we're trying to find out is what is the fair amount that each one of them should get so they get paid adequately for their time compared to the other person. Do you understand the problem at play here?
Wait, so both of them together made $176?
Right. Right. That's $176 for the project. Total money paid. So they did it together, but they didn't work the same amount of time. We got to find a way to split up the $176 to make it fair. Okay. And it's not very clear, right? It's not like one of them worked double the other one, right? I mean, the ratios aren't that clean. They aren't that pretty. There are two ways to compare this problem, and they go back to the idea of ratio. Do you remember what we said we could do for ratio? What were our two ratio options? Very first thing, very first slide. There's two ways to do ratios. Part to whole is one of them, and part to part's the other one, right? So I'm going to show you how to set this problem up for both of these. There are benefits and there are sort of drawbacks to both methods for this one. The part to part is the easier one to see at the beginning, but maybe not the easiest one to solve at the end. So let me show you. So let's take a look at what we would do if we set this up as part to part. So if we're thinking of this as part to part, what we're doing actually is we're going to compare Sheila and Dora. How much money they each made, how much time they each worked. Okay? It's their part of the project. Does that make sense? Okay. So Sheila's listed first, so we'll put her on top. Sheila compared to Dora. And we're comparing basically their hours to their pay. Right? So we'll put hours on the left and pay on the right. So how many hours did Sheila work? 3.5. And just for complete simplicity, we're just going to write 3.5. We're going to be cross multiplying with it in a minute anyway. How much did Dora work? 4.5. Now here, that part's the clean part to see where it would be set up. I mean, you knew that to begin with, probably. That's a good comparison. The problem is you don't know how much either one of them made, do you? But you do know how much they made together, yeah? So what we can do is we can say that Sheila made X. So let's just take a number for a minute and you think with me. If I told you that Sheila made $50, how could you figure out how much Dora made? You would take 176 and what would you do? You would minus the amount that Sheila made. And that's exactly what you can do with letters, with variables here. Whatever Sheila made, Dora made the rest. And they made a total of 176, so you can take the 176 and you can subtract whatever Sheila made. So there really is just one variable here because we do know that they in total made 176. So what we can do then is we can cross multiply this. The one thing that makes this a little bit trickier is number one, figuring out that it's x and 176 minus x. But it's also that you have to remember when you're cross multiplying this that 3.5 distributes to both the 176 and the x. So don't forget the distribution. And let me actually write it down this way just to remind you. You don't have to write that down, but you could. That we need to distribute that through. So what is 3.5 times 176? What is it? 616 minus x, I'm sorry, I didn't do it already, minus 3.5x, right? So distribute the 3.5 equals 4.5x. Now what? Good. Add 3.5x. Okay, so what is 4.5x plus 3.5x? 8x. Now what? Divide by 8. What does x equal? 77. Now, we need to answer the questions asked. The questions asked, how much did each earn? So x is what? What does x tell us? That x tells us how much Sheila made. Sheila made $77. I don't need to do a lot of work to find Dora. What do I have to do? Subtract. 176 minus 77, and what do I get? 99 is correct. So Sheila made 77, Dora made 99.
Could you just add up the total hours, which would equal like 8 technically, and then divide that by...
Oh, Anne-Marie, you're ahead of me. Yes, that's the other way to do it. Excellent job. That is comparing part to whole. And the algebra with it is cleaner. But it's not usually what people think of at the very beginning. So that is perfect. Yes. So part to whole will be comparing one of their portions to the whole that they all did. So we can pick a person. We'll pick Sheila. But we could just as easily pick Dora. We're comparing Sheila to the total. So Sheila worked. Again, we're still comparing hours to pay. Okay, so that part's still the same. So Sheila worked was it 3 or 4? Which one's hers? 3.5. Thank you. 3.5 hours, excuse me. And the total number of hours, just like Anne-Marie just said, that they worked was 8, right? The total number of hours is 8. We want to figure out what Sheila made, that's X, and then the total they made was 176. So there's no distribution when we do this, which definitely makes it a cleaner system to solve. So then I just need to do 3.5 times 176, which you guys just did a minute ago, so I'll cheat and tell you it's 616. And then 8 times x is x. So we still end up finding out the same answer, but we did a different comparison at the beginning, didn't we? X is representing the same thing in either case, actually, too. It's still representing the amount Sheila made. But the comparison is different. Sheila compared to Dora or Sheila compared to the total. Does that make sense? And neither one really is all that much harder. I mean, if you see one of them, just go with it and you can solve it. You're going to be able to deal with it. But the second one that we just did, which is actually on the left-hand side, was a little bit cleaner. Any questions on that? Okay. This one's an interesting one. There's more than one part to this one, so let's take a look. At Rattlesnake School, the teacher-student ratio is 1 to 30. So that means for every one teacher, there's 30 students, right? If this school has 1,200 students, how many additional teachers must be hired to reduce the ratio to 1 to 20? So what are the things that are being compared here? Students and teachers. They did teachers to students, so I'll put teachers here. And is it okay if we put students as a denominator for things? Is that okay with you guys? And basically what we're comparing is the ratios that we're given to the actual number of students, the actual people. Okay. The ratio of teachers to students is what currently? 1 to 30. So that's 1 over 30. And then, let me actually write that in a little bit differently. This one teacher, just like we said, to 30 students. So what do we know aside from that? There are 1,200 students. So we can use this first original ratio to actually find out what? How many teachers we actually have right now. So we have X teachers now. So this situation is what's happening now, currently. So what do we have to do? Cross multiply. So if we cross multiply, what do we get? Good. 30x equals 1,200. And then divide by 30. Good. And that gives me 40 teachers. So this is how many we have now. Now that's not exactly the question that was asked, was it? What was the question asked? How many new teachers we need to hire so that what happens? The ratio is 1 to 20. So how can I find that out? Right. We can set up another proportion that's 1 to 20. It's still 1 teacher to 20 students. So the teacher and student part's the same. And nothing indicated that the number of students was changing. So that's still 1,200 students, right? Now I'm going to call this Y just because I don't want to confuse the fact that I already used X. It's not the same value. It's something different. So this is going to be Y teachers. That is how many teachers I want to have in my school. And I would solve it the same way, right? So instead of having 30, I'd have 20, and then it would be Y equals to 1,200. Divide by 20. What would Y be? 60 teachers. Now the question asked me what? How many more teachers must be hired? So what would the correct answer be based on the work you've shown?
20.
We need 20 more teachers. Right now we have 40. What we really want is 60. That means we're 20 short. Who thinks they're hiring 20 teachers? Probably not. All right. Mary's working with measurements, and she writes up the following proportion. 12 feet to 1 foot is equal to 5 feet to 60 inches. How would you help her? Okay, so Shelby, what you're saying right now is that there's something that's not matching up quite right, yeah? Yeah. So what's not right is that I don't have the units in the same spots. I won't say right spots, but in the same spots, right? So these fractions are actually correct fractions, aren't they? I mean, 12 inches really is 1 foot, and 5 feet really is 60 inches. So those ratios are correct, but they're not set up in the correct proportion. Is everybody following that? Okay, so we might want to say something like that to her. So you guys know, because I've told you before, that I always like telling students what they did right before they tell them what they did wrong. I really try to do that when you come see me in my office too. So if I don't do that, you tell me that I need to practice what I preach, okay? I need to remind myself when I work with my children at home too, right? So the ratios are right. Individually, right? The individual ratios are correct. But the proportion isn't set up correctly in the right pattern. Something of that nature would work. What we need is we need the units to be in the same, I'll call it location, right? The same place, either are both on top or both on bottom kind of thing. So you could say, for example, 12 inches over 1 foot equals 60 inches over 5 feet. Or what else could she do?
Inches on the sides.
Yeah, she could do 12 inches over what?
60.
Over 60 inches equals 1 foot over 5 foot. That'd be another option. And there's 2 more options after this. I mean, there's 4 options total she could have that are actually different. You could flip them up, flip each of these, you could flip over and get the reciprocals of them and they would work too. Yeah. Good. All right, does that make sense for everyone? All right. I mentioned this sort of in passing earlier, and so now we have a specific example that does exactly what I was talking about before. Amy's friend told her that the ratio of boys to girls in her first grade classroom is 5 to 6. Amy was very surprised that her class would have only 11 students. What would you tell her? So first of all, where did she get the number 11? Let's talk about that.
She added the girls.
She added the 5 and the 6, right? So first of all, is it possible the class has 11 students?
Yes.
Yeah, I mean, that could happen, right? For a variety of reasons. Perhaps it's a special ed classroom. Perhaps they hired an additional teacher because the classes were just slightly too large to begin with. I mean, like, it legitimately could be 11, right? So it possibly could be 11. If it's not, what else could be going on? Yeah, the ratio could have been reduced. That's exactly right. So a ratio of 5 to 6 is equal to what other ratio? Give me another one.
10 to 12.
10 to 12 or
15 to 18.
15 to 18, and you could write ... At that point, you've probably got something a little bit too large if you go one bigger for a classroom size that at least for the classrooms that we deal with here in the U.S. So 5 to 6 or 10 to 12 or 15 to 18. So one thing we might want to tell her is that all of these ratios reduce to 5 to 6. Okay, they're all in 5 to 6. Meaning the class could have 11 students, or what else? Or 22 students, or what else? Or heaven forbid, 33 students. Bless your heart if you're in that classroom. I hope they give you at least 2 8s. You might need it with 33 kids. That's a lot of kids in a classroom. And we could actually keep increasing. We could talk about this being 44 or 55 or 66 because that would be the additional ratios beyond here that are equal to the ones that we have. Okay? Does that make sense to everyone? All right.